Welcome back. Till long day after, today I will discuss dense subset of a metric space. This topic actually very important for higher study. What is the dense subset of a metric space? Today I will discuss this property. Also I will discuss the dense subset of a metric space. Today I will discuss this concept, also some property about this topic. At first say, what is the definition of dense subset? We all of us know dense subset means a subset A is dense when a closure equal to the main set X, then this subset A is called dense set. But today I will discuss what is the geometry about this part. This for dense subset, why a closure equal to X. Today I will see what is the actual geometry about this concept. Consider the metric space X and consider the set subset A which contain the point this. Okay, actually this subset A of the metric space XD is dense. Whatever ball you will take inside the point X, always it will intersect the set A. That means B of X are intersection A not equal to phi, and this is true for all r greater than 0, because whatever ball you will take, always it will intersect the point. One definition is a subset A in the metric space XD is dense in X if for all X belongs to the metric space X, X is a limit point of the set A. That means actually for we all of us know what is the definition of limit point. For all r greater than 0, there exists point, at least one point in the set A, consider this point is M, such that this ball B of X r contain the set A. That means for all X in the metric space XD, if we take one ball, whatever radius you will take, always there exists a point in the set A. So always this ball intersect the set A. So B of X r always contain the subset A. That means this is actually the definition of limit point. That means this X actually limit point of the set A. I hope my all viewers have understood why in graduation we all of us taught definition of dense set means a closure equal to the set whole set X, because dense means every point is a limit point of the set A. Therefore actually a subset A of a metric space XD dense in the space X, if every non-empty open set intersect the set A. Every non-empty open set intersect the subset A means consider an arbitrary point X in the set X, and here consider the radius r equal to epsilon. Consider this distance equal to 1 over n. Then B of, here the ball with respect to the point x with radius 1 over n. Since B of x comma 1 over n intersection A not equal to phi, that means consider there exists a sequence an belongs to B of x comma 1 over n intersection A. That means, and from this expression we can tell actually an converges to x, where this x is a limit point of the set capital A. This is true for all x in the space, metric space X. Therefore, for all x, there exists a sequence an such that an converges to x. So, all limit point is called closure of the set, which is denoted as a closure. Therefore, a subset of the set X is dense in the set X if a closure equal to the whole set X. If a closure equal to the whole set X, then the set A is called the dense subset, and this definition we all of us know. A subset A is dense when a closure equal to X. But I hope my all viewers have understood now why dense means a subset A is dense, why this means a closure equal to whole set X. Okay, and this is if and only if condition. If a closure equal to X, that imply always the subset A is dense in the set X. Because if one element X, consider one element X belongs to X, and since a closure equal to X, obviously this is equal to a closure, and by this expression we can tell X is a limit point of the set A, and since X is a limit point of the set A, that imply B of X at intersection A is not equal to phi, and this is actually definition of dense set. So a closure equal to X means A is dense subset in X, in the set X. Means A, which is subset of the matrix space, is dense if and only if, this condition is if and only if, a closure equal to the whole metric space X. Then actual definition of dense subset, dense set is, let A be non-empty subset of a metric space X, D. Then following statements are all equivalent. 1. For every X in X, row of X, capital A, where A be non-empty subset of a metric space X, D equal to 0, and row of X, A equal to 0 means infimum distance of D of xy such that y belongs to A equal to 0. Second, a closure equal to whole set X. Third, A has non-empty intersection with every non-empty open subset of X. And fourth, A, which is the subset of the metric space X, then A is dense in the space X if for all X belongs to the capital X, then there exists a sequence AN in the set A such that AN converges to X. And in nonlinear space, this definition is such type: a set capital A is said to be dense set in nonlinear space X if for each element X in the nonlinear space X and for every epsilon greater than 0, there exists at least one point A belongs to capital A, such that here, since nonlinear space, therefore norm of X minus A less than epsilon. This is the definition of dense set in nonlinear. Now let's see some example of dense subset. First example, rational number Q is a dense in the usual metric space R. Why this is dense? Because for all points C in the metric space R, there exists R greater than 0 such that BCR with intersection Q not equal to 5. So Q is dense in the usual metric space R. Similarly, irrational number R minus Q is dense in the usual metric R. Third, the set A which contain A plus IB which belongs to complex number such that AB belongs to rational number is dense in complex number, because this is dense because here A closer equal to whole complex number. So this set is dense in complex number. Fourth, the set Qn which is actually equal to Q cross Q cross Q. This is actually dense in Rn with usual metric space. Fifth, consider A equal to open interval 0, 1. Obviously, this set is dense in the space X equal to close interval 0, 1, because here A closer equal to close interval 0, 1 which is equal to X. So, A is dense in the metric space X equal to close interval 0, 1. Okay? I hope my all viewers have understood this concept. Consider discrete metric space and consider one subset M which is the subset of X. Is M is dense in this space X where X is discrete metric space? That means we have to prove M closer equal to X. In discrete metric space, we all of us know d of xy equal to 0 when x equal to y and 1 when x not equal to y. If we consider one point x which belongs to x, omitted capital M, that means consider one point x which does not be member of capital F, that means x, small x be the member of capital X omitted with M, then distance between x and small m, where small m be the member of capital M, would be 1. So, if we consider one ball around the point x of radius half, then there exists no point of the subset capital M. So, any ball of radius half around the point x does not intersect the subset M. So, M closer does not belongs to whole x. So, M is not dense in discrete metric space X. So, only dense subset of the set X is X itself. I hope my all viewers have understood this concept. Okay? OA. Our next example is LP space. We all of us know what is the LP space. LP means actually this is the infinite series which is convergent. And here the subset A is collection of sequence whose n term is finite value and other term is 0. We have to prove this subset is dense in the space LP. For this, at first consider two elements x and y belongs to LP and we have to prove a closure equal to LP. For this, consider this is x be the arbitrary element of LP and let epsilon greater than 0. Then there exists positive integer capital N such that since this is the convergent series, therefore after the big term n, I equal to n plus 1 to infinity, absolute value of xi to the power p would be, since this is the convergent series, this is less than epsilon to the power p over 2. And since rational number q is a dense in the space R, therefore for every real number there exists a rational number which is close to it as we wish. Now consider one element from the subset capital A. Since the subset A is look like such type, therefore the element would be, choose the element small m equal to a1, a2, an, and after this n term is 0, consider this element m belongs to the subset capital A. Now distance between the point x and m would be dp, since the metric space it belongs to dp, so consider dp to the power p equal to summation I equal to 1 to n x absolute value of xi minus mi to the power p plus summation I equal to n plus 1 to infinity xi to the power p. Obviously this is less than epsilon to the power p over 2 plus this first also less than epsilon p over 2, because from this expression we can tell this. So this is equal to epsilon to the power p. Therefore that imply dp x comma y less than epsilon, because here dp to the power p, sorry here xm not y, xm. Therefore from this expression, since this is less than epsilon, where m is the element of capital M and x be the arbitrary element of LP, since this distance is less than epsilon, by this expression we can tell rho of distance between x with a, infimum distance always would be 0. Therefore by this expression we can tell a closure equal to holes place LP. Therefore the subset A is dense in LP. I hope my all viewers have understood the proof. Okay? OA. Now I will see new set C of AB. We all of us know, so what is the C of AB? C of AB is continuous function defined on the closed interval AB. Now you have to prove the set PAB, which is actually all polynomial defined on the set closed AB, with rational coefficient. We have to prove this set is dense in CAB. Now here I will apply the actual Webster's approximation theorem. We all of us know Webster's approximation theorem. Just recall. In one variable, we all of us know, if f defined from closed interval ab to r, which is continuous function, then always we can find a polynomial Pn such that Pn converges to this f uniformly on this interval, closed interval ab. This is the Webster's approximation theorem, and in higher dimension, in nonlinear space, this theorem is such type: given any epsilon greater than 0, for every ft belongs to CAB, means continuous function which is defined on closed interval AB, then there exists a polynomial Pnt such that norm of ft minus Pnt less than epsilon, and this is true for given any epsilon greater than 0. Proof: consider a function f which belongs to C of AB, then by Webster's theorem there exists a sequence Pn of polynomial with real coefficient that converges uniformly to the function f on the interval AB. That means for each epsilon greater than 0 there exists a positive integer capital N such that for all t belongs to closed AB, distance between Pnt minus ft less than epsilon, and this is true when n greater than equal to capital N. That imply from this expression we can write this is actually d infinity Pn comma f less than epsilon. This is true for all n greater than capital N. But any polynomial can be uniformly approximate by a polynomial with rational coefficient, and since Q is dense in R, therefore corresponding to the sequence Qn of polynomial with rational coefficient such that absolute value of Pnt minus Qnt less than 1 over n, and this is true for all t belongs to closed AB. Have you understood? From this expression we can tell set of all polynomial who is defined on closed interval AB with rational coefficient is dense in CAB. That means P closure AB whose coefficient is rational is actually CAB. That means set of all continuous function who is defined on closed interval AB. I hope my all viewers have understood this question. Why set of all polynomial with rational coefficient is dense in the metric space CAB? This is actually use of Webster's approximation theorem. If you know the Webster's approximation theorem, then you will understand in better way. Okay? Well, today I will stop here. In my next video I will discuss what is the know-what dense set. Actually this type of concept very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.